All right, our next speaker is Mitch Griggs. He's Vice President of Environmental Services for Duke Energy.
Thanks, Mike. Good afternoon, everybody. I'm the beginning of the home stretch for today, and so I'm kind of glad to be in that position for you. Like Mike said, I'm Mitch Griggs. I'm the Vice President of Environmental Services for Duke Energy. And I think Mike did a good job in his presentation before the break, really kind of setting up what I'm going to talk about for a few minutes now. And that is, how do you achieve an integrated environmental compliance strategy dealing with everything that we have to deal with? My little legal slide there that says I'm going to be sharing a few things with you later on that are simply estimates and projections, and so I'll move on beyond that. Give you a little background about Duke Energy for those of you who may not know who we are. We are a company headquartered in Charlotte, North Carolina. We have recently merged with Progress Energy. Progress was headquartered in Raleigh, North Carolina, to form our new company. You can see the financial numbers there in terms of market cap and operating revenues and assets and so forth. But we have 29,000 employees in our new company. Around 58,000 megawatts of generation. And really we have a pretty diverse mix of generation. We have nuclear, coal, gas, hydro, pretty good blend overall, gas and coal. A little bit more coal than we have gas, and about 11,000 megawatts of nuclear. We're also in the renewables business, at least a little bit. We have about 2,000 megawatts of renewables generation, wind and solar, across the United States. We continuing to grow that business a little bit. We have an international presence. That's Duke Energy International in Latin America, where we operate in 6 or 7 countries down there. Have about 5,000 megawatts there. As the slide says, we have 7 million customers across the U.S., and the map shows our service territory in the U.S. across 6 states. I mentioned the merger. It's going pretty well. We're about 4.5 months into it now. We are working through the cultural issues that are really beginning. You know, in my experience, a merger of this nature, of this size, it takes quite a few years to really kind of bring the cultures together. We're in the same industry, doing the same business, generating the same product, same types of customers. But exactly how we do things, the nuances, is where you really get into the cultural matters, and we're working our way through that, integrating those cultures. We had last week we reported our first quarterly earnings as a combined company. Worked out pretty good. So we're excited. I think the future of Duke Energy is bright. We've got a few hurdles to get over that are regulatory in nature, but we are working our way through that. Mike showed you a similar type slide, and all I want to do with this slide is just throw it up there as an at-a-glance slide and make a couple of points. You know, these are the proposed or final regulations that our industry is dealing with right now. And it's only some of the things. We've got other regulations coming at us that Mike talked about that are still ahead of us, things like the effluent guidelines and things of that nature. But this confluence of regulations, as you all know, is unprecedented in our industry. In the past, you know, we would have an air regulation that we had to deal with, and we'd work our way through that. We'd have a water regulation, and we'd work our way through that. But for the past couple of years, these things have just been coming unrelentless. Somebody on my staff called it the tsunami of environmental regulations, and I think that really kind of summarizes it very succinctly. Very, very challenging, and I'm going to talk a little more about that. But the cumulative effect, of course, of all these regulations coming at us and the intersection of all these regulations is really going to, it is and will continue to reshape our industry as we go forward. So how do you achieve an integrated compliance strategy that's reliable, cost-effective, truly integrated when you're dealing with all these different regulations that are occurring simultaneously, all of them with changing outcomes, And in fact, we're involved, and many of you are involved in trying to shape the outcomes to the best of our ability to make them as balanced and flexible as we can. But how do you achieve that compliance strategy with that? Air, water, waste individually, and then the interrelationships between those different media, extremely complicated. Our framework, the approach that we've been taking to get our arms around this is really twofold. About a couple of years ago, we put a team in place, a team of environmental folks, engineering folks, operations folks. That was the genesis of the team. We call it the Environmental Compliance Implementation Team. I'd like to say, we're very fortunate in the fact that I think we've got some very talented folks in our company that we were able to bring together to work on this. And some of the folks are here in the room with me today. I encourage you to seek the Duke folks out and have a conversation with them this evening or through the day tomorrow. But the team was pulled together to begin looking at this, what was out ahead of us, and to put a process together, a process to drive solutions and a strategy for how do you deal with all these different regulations simultaneously. And this is the process that I want to talk a little bit more about this afternoon. At a high level, this is a summary of that process. This is our compliance planning effort. The process is a multi-step iterative approach that we use. It utilizes economic modeling and project development data. It accommodates a wide range of factors and inputs and circumstances and things of that nature. And it really kind of organizes all that and prioritizes that and spits out information and outputs so that we can make good decisions. You can see there the chevron chart that we've got, 5 different steps. But under the assumptions and scenario development, this is where we interpret the regulations and determine possible options and costs of those options and capabilities of those options from a performance standpoint when you're looking at different equipment. We build in, as a second step, the market fundamentals, looking into the future around energy prices, fuel prices, and so forth. We make sure that's baked into our process. Then we do screening models. The screening models really determine the optimal method to make sure that we're outfitting our units correctly, the most optimal approach that we can come up with. We pass it then over to our resource planning folks and integrated resource planning for them to do an analysis. They're taking information from the screening models. They're applying their specific models to really make a determination. Does it make sense to control and retrofit the units, or does it make sense to retire the units? And then finally, we come up with a plan recommendation that is designed to determine the least cost, the most feasible plan that considers all the different factors, including the political realities that we deal with around things like rates and so forth. So what I'm going to do is spend a little more time talking about each of these 5 steps this afternoon. So under the assumptions and the scenario development, interpreting the regulations, kind of reading the tea leaves, we get involved with that early on. Before the regulations are even proposed, we're looking at what's coming down the pike. We're trying to influence that as well through our company, through industry associations and whatnot. But we're getting a glimpse of what the future might look like from a pre-rule standpoint. Then the rules are proposed. We go back and look at the proposed rules and how they may have changed from what we thought it was going to look like. And then the final rules when they come in, just like MATS did. And MATS changed significantly from when it was a pre-rule and what we thought it was going to look like to the final rule. And that made a huge impact on our compliance strategy around that. As part of this step, we also began considering the broad range of equipment that we need to put on. What's the major pieces of equipment? Scrubbers, SCRs, bag houses. The minor stuff, chemical additives, reagents, and so forth. What types of coal are we going to be burning? We heard earlier in one of the presentations about the differences between the coal makeup from the different basins across the U.S. So, looking at that around sulfur, mercury, chlorides, things of that nature. Then we start projecting the costs of all these compliance requirements, the capital investments, and the O&M investments. And the O&M investments, we're looking at fixed O&M and variable O&M. You know, fixed O&M like resources of staffing and so forth that you're going to have on site to operate the equipment. Variable O&M, what kind of chemicals are you going to use? Somebody talked about the coal variations as a variable O&M. These are the things you start looking at. So reagents and sorbent injection, continuous emission monitors, how are you going to deal with your ash? What kind of wastewater treatment options are you going to have to deal with? Around 316B, because we're looking here at all the different regulations, not just the air regulations. So what are we doing with regard, what will we do with regard to fish impingement and entrainment? Screens, modifying our intakes, doing studies to deal with that. And then, of course, ash basin closures. And as we've looked at this, the ash basin closures, after we're down the road a little bit on our air initiatives, the ash basin closures are going to be extremely expensive in our judgment as we go forward. But the bottom line for this step is we really went through the modeling process to put the information together to really bound our different scenarios. A light case, a strict case, and then a most likely case scenario. And it's the most likely case scenario that we took forward to really look at what the costs were going to be. And the second step of our process, this is where we bake in the market fundamentals. So we're going out and we're gathering information from national economic models. Most of us are familiar with those. And we're forecasting energy demand, production, things of that nature. We take that information, refine it by applying what we believe applies to Duke. So we look at, we consider our institutional knowledge, we use that to add on and refine the numbers and information, and then we look at it from a regional standpoint as well. But we're looking at the forecasted commodity inputs around energy, fuels, emission allowances, and so forth. What does the future look like with all of that? And then that becomes inputs for the next part of our overall process. This step really helps us determine the value of the asset when it's outfitted in a particular way with particular and specific equipment, and how that relates to the future of dispatching that unit into the future. And the third step, we're going through a screening process, a screening model, if you will. Again, taking the market information that I just spoke about, but then we're running multiple scenarios through our modeling processes to screen the economics and the new equipment, looking at different combinations, different configurations, what works best for a specific unit. And depending on where the unit is in the United States, the combinations and the configurations are much different. We might run 200 different scenarios or iterations around a particular unit, finding different alternatives and alignments that make the most sense. What are the chemical additives that we want to put into the system, and where do we want to inject the chemicals? It allows us to determine the most efficient configuration for a particular unit. You know, it predicts the output of SOx and NOx and water and waste emissions, and it does it in a way that allows us to really understand what's going to impact this unit as we go forward. The main objective here, of course, is to ensure that the way that we put the equipment on and we run the equipment through a modeling scenario, that it's going to achieve the expected outcome that we need to comply with the regulations. We then hand the outputs of our model over to the resource planning group to do their integrated resource planning to determine if the controls that we've identified and the configuration that we've identified, if that's really cost effective, or does it make more sense to retire and replace the new generation, and retire and replace the units and then with new generation. They're looking at typical considerations around resource planning, so reserve margins, remaining life of the control unit, looking at the various risk analysis aspects of that. But they are looking for the lowest cost, the best option for our customers. Of course, the bottom line is, do you retire or do you control? And then finally, we make the plan recommendation. So the point here is that models, they don't make decisions, they only inform decisions. And your models are only as good as the information that you put into the models. At this step in our process, we're pulling all the internal stakeholders together. So we've got our engineering and our environmental folks and our operations folks, but we're re-engaging the folks from fuels and resource planning and legal and accounting, governmental affairs, rates and regulatory affairs, all the different players who are key to help us make the right decision on a unit-by-unit basis. Then we're going back at this point and really kind of verifying again, really after we come up with an idea as to what the best configuration is for a unit. You know, we're getting that information about what's the knowledge that we have specifically about that facility. What kind of operating experience do we have? Are there any specific site related constraints that we have, construction constraints? You know, can you really build that bag house on that site? If you want to put SCR on that site, do you have the space to do that? We had one situation where we were configuring an SCR and we didn't have the ground to put it on. So at that point, we were deciding to put it up on stilts. And you can think about the costs associated with that, with hovering an SCR above other equipment and the challenges associated with that. But these are some of the things and some of the challenges that we were actually looking at. When you're picking that best plan, you're going back and you're looking at the condition of the unit. You know, is it simply worn out? Is it time to move on? What's the investment that we've had in that unit, the remaining useful life, depreciation? And you also look at tax considerations here, because that factors in as well. And of course, you go back and recheck your fuel types and availability, and this is where we would reconfirm, can we do any fuel blending? We call it Fuel Flex at Duke Energy. How can we mix fuels from different bases, from different sources to help that, to let that help achieve our limits that we're looking for? The plan recommendation that comes out of this is to find the least cost, the most reasonable, the most feasible, and a robust plan. And when I'm talking about a robust plan, I'm really talking here about what is the margin of compliance that this plan for this unit will achieve for you. Are you really close? Or do you have a wide range of compliance there? You need to look at that because you really don't know what's coming down the tracks with regard to future environmental regulations, and that's something you have to factor in. But you also have to look at the jurisdictional policies and the politics that are going on. It may be different as to what you need to do in Indiana in our situation versus Florida. And you have to look at timing too, as it relates to rate cases and things of that nature. It's a pretty complicated process. And every step of the way, we have the tools and the means to go back in and run additional iterations, to cycle back and make changes and make tweaks and adjustments as we need to on a unit-by-unit basis, plant-by-plant basis, jurisdiction by jurisdiction. And it's worked really well for us. Like I said when I started, we still have regulations coming at us. We don't know what the final end game is going to be for many of these regulations. CCR, what's that going to do for us or to us? 316B, effluent guidelines. With the new administration, still a question mark as to how this is going to play out. Many of us think it'll come pretty hard at us after the first of the year. So things that we thought might be delayed a little bit, like CCR, we think it may come at a faster pace towards us. Based on what we know and the models and the iterations we've been going through, our estimation is that by 2016, we will have about 50% fewer coal units in our fleet than we had last year in 2011. That's retiring somewhere around 6,000 megawatts of generation. Now these are, of course, smaller, older units. So when you're looking at units, not all units are created the same, as all of you know. but that's still an awful lot of generation that is being retired and replaced. And most of it's being replaced with gas, quite honestly. When you're getting rid of these units, these smaller units, I believe there's an issue around reliability that starts creeping in. If you've got if all you have left around coal generation are your big units, 800,000 megawatt, 1,200 megawatt units running. If you have a forced outage or something like that, what's your backup? Hopefully you've got gas or something like that, or you can buy it off system. But I think in the past, we've had smaller units we can bring on. We're not going to have that luxury as we go forward into the future. And you can see the last point here is that we estimate that over the next 10 years that we will potentially spend between $6 and $7 billion. We just published our SEC report, our 10Q, and this is what we had in there. This amount of money was based on the modeling and the screening and everything that I just talked about that we came up unit by unit, plant by plant. That's a significant investment going forward, particularly when you look at the fact that probably as of right now, and I'll speak just for the former Duke Energy Corporation, we probably spent up to this point $8 to $10 billion over the last 7 or 8 years coming to where we are today, and the former Progress fleet doing the same sort of thing. So with that, that's my points for this afternoon. Definitely a challenge ahead of us. We're going to continue to work to do our best to influence these regulations that are remaining, to try to get the most flexible outcomes that we can. But we feel pretty good that our process for determining the cost and what we need to do to put the equipment on has been working pretty well for us in the past. So with that, that's all I have. Thank you.
Anybody have a question? Yes.
Yes. When we retire the units, our plan right now is to fully decommission. That's the path we're on today. Now, I will tell you that at this point, we've probably only decommissioned, I don't know, maybe three plants total of, I'm going to just guess, say 10 units, small units around the U.S. So we've got some experience in that, but our intention would be is to bring those units down to ground level, basically, tear them down. And then deal with whatever we find beyond that. But those decisions we made on a case-by-case basis. But as I stand here right now, I think we've headed down that path at 3 or 4 of our plants. Any other questions? Okay, thank you.
Okay, our next speaker is Brandon Looney, who's Environmental Controls Research and Development Manager at Southern Company.
Thanks. The topic here that I'm going to talk about is why you may not comply with the Mercury Standard. And that might be a bit of a strange title to a presentation, but I recall early this year I was attending an EPRI meeting. I think it was in February, and I left the meeting, and as you can imagine, the majority of the discussion in the generation environmental controls area was about MATS. And everybody began to give their thoughts about MATS from the technology standpoint and talked a little bit about compliance plans and strategies. And I got back to Birmingham and I started talking to my management, and they were asking, what did you think of the meeting? What are other people doing? And I said, I just have this feeling that people are going to have a hard time complying with this Mercury Standard, that there are going to be people that have compliance issues that are out of compliance from time to time. And so the point of my presentation today, because I made that statement based on feeling, and I wanted to sort of try to see if I could articulate what it was that drove me to that feeling back about 8 months ago. So this is my small disclaimer. This presentation is not a critique or an endorsement of the MATS rule. And it's not a representation of Southern Company's position on the validity or the content of the rule. In fact, I'm going to try to say nothing controversial about regulation. I'm going to try to say some controversial stuffs about mercury. So I'm kind of a MATS mercury junkie. That makes me a nerd, and I'm okay with that. But I really have sort of three messages. If you're a utility person, my message is really a warning. Mitch said that models, and I would extend that to planning processes, are only as good as the inputs. And we have these sort of basic assumptions in our inputs that if I build technology X or Y or Z, I'll comply. Okay, I'll warn you, well, what happens if you build X, Y, and Z and you don't comply? And I think the risk of that happening on mercury is much greater than our traditional pollutants. So we'll talk a little bit about that. If you're a technology person, my message is really a challenge. Can you acknowledge that we still have some areas of improvement and help us solve that? If you're a regulator, then my presentation is a request that you understand the challenges that we still face on these regulations. So, why may you not comply with the mercury standard? I really just want to talk about three things. First of all, mercury behavior is inherently complex, and we'll talk about that a little bit. It's more complex than the traditional pollutants that we talk a lot about, PM, NOx, SOx. I would argue that it's even more complex than CO2. Maybe not as costly, but it's more complex. Secondly, that mercury emissions are observed to be highly variable. And I'll show some information, some backup, the proof of why we believe that to be true. And then thirdly, mercury control performance, the technology performance can be unreliable. And I struggled with that word unreliable because I knew I'd have some mercury control technology folks here in the room that say, oh no, our technology's not unreliable. So I'm not saying that any particular technology is not good technology. In fact, I'll show some data from technologies that give unreliable performance, but I still think they're good technologies. We just need to be prepared to deal with the aspects of those technologies that can be unreliable. So these are my main three topics, and we'll just step through them one at a time, and I'll show you some evidence that we've seen at Southern Company that lead me to believe that these three truths about mercury give us a risk that although we have a great plan in place, maybe we have sufficient time, maybe we make the right economic choices, but what's the risk that we find ourselves with some compliance issues? Talk a little bit about mercury behavior and its complexity. Now, John had a couple of presentations in the NALCO presentation that had all these equations on it, and I don't want to go there because that would just expose me and confuse you. So I'm going to try to make the complexity part simple if that's not a conflict there. But there's really two things that we need to think about when we think about the complexity of mercury behavior, or really mercury behavior at all. Or I'll boil it down to two things: oxidation and capture. So a lot of stuff is going on in the flue gas, but if we could just concentrate on oxidation and capture, then I think we would understand the bulk of what's going on. And so I drew a real simple cartoon here of a power plant kind of lineup: boiler, SCR, ESP, scrubber, and then what could potentially happen with oxidation throughout this path that mercury takes. The interesting thing is the most confusing chemistry that happens in a power plant is in the boiler. There's all kind of stuff going on in combustion. But what happens from mercury in the boiling is pretty boring. It's just volatilized, and it leaves the boiler as elementary mercury. So that part of it is actually rather simple. We just see there the percent oxidation is 0. It leaves the boiler. Most all the mercury in the fuel is volatilized. Pretty easy to understand. It gets real difficult from that point forward because we see these divergence of possibilities of what can happen with mercury oxidation. You hit that SCR, and things start to get interesting. And I just kind of show there, the green line is good, the bad line is less than good, and all the area in between is the potential world of possibility. So generally speaking, as you move along the gas path, oxidation continues to increase. That's good because we're pretty good at capturing oxidized mercury, and we're pretty bad at capturing elemental mercury. So you can see this potential that across an SCR, you can get good oxidation, up to 90%. And then you cross through the air heater, which I didn't draw on my cartoon, and the ESP, you get some more oxidation, and then it ends the gas path as highly oxidized. I mean, we observe greater than 95% oxidation at many times. But there's also the possibility of the red line, the bottom line, the thing that isn't necessarily advantageous for us, and that is limited oxidation across an SCR, no additional oxidation anywhere else in the system, and then reduction in an FGD system. And because these things are possibilities and not just theoretical possibilities, but they're observed behaviors of mercury, you're left with this whole space in between those two lines that happen each and every day in our plants. And that creates a very unique and complex behavior. SO2 doesn't behave that way, right? SO2 is made in the boiler, and then it just stays SO2 until you get ready to capture it. NOx is made in combustion, and then it just stays NOx until you intentionally do something to change that. PM released from the coal and stays PM. So we have this odd complexity with mercury that we have to deal with. So to kind of wrap that up, well, how does oxidation and capture, what's really going on in the boiler, as I mentioned? Mercury volatilized into the elemental state, simple. Then the SCR, maybe the most complex piece in the train, what goes in the SCR, a lot of oxidation, but it's dependent on a lot of variables. How much halogen do you have in the flue gas? What's your flue gas temperature? What's the activity of your catalyst? How far through the reactor does the ammonia penetrate? There's probably some more, but I think that's enough to make the point that it's really complex what's happening there. And then the ESP. The ESP can capture a portion of the oxidized mercury. Doesn't mean it does capture it, but it can capture it, and it's also dependent on multiple variables. Temperature, again, plays a role, the properties of ash, how much unburned carbon you have. So you're adding on more complexity. And then lastly, the FGD can capture oxidized mercury, very good at capturing oxidized mercury, but you have this whole reduction potential going on, the big bad mercury emission back to elemental state and out your stack. So the thing that this creates is the reality that mercury capture can range from 0% to over 90% in very similar systems. In plants that deploy the same technology, you can get close to 0% or over 90% control. And I think that highlights why mercury is different than a lot of other pollutants. There's no plant out there with a scrubber that gets 0% SO2 removal. But there probably are some plants out there with scrubbers that get very close to 0% mercury removal from time to time. So, mercury behavior, very complex. That's sort of my first point. Secondly, I want to talk about mercury emission variability. If you've had the misfortune of hearing me speak any before, this is probably a topic you've heard me talk about. I've carried this silly slide all over the country and bored many people in rooms like these with it. But what we see here is mercury emission data from our units that have SCRs and FGDs. This is SIMS data over several years, and what it shows is the emissions are highly variable. So what we've done is we've taken actual emission data, and we've calculated 30-day rolling averages, just like the MATS rule would ask us to do, and then we just statistically compare our historical performance to a MATS type of regime. And so you see from plant to plant, there's 7 plants here. We have anywhere from 400 to over 1,000 individual 30-day averages for each plant. If you look at the mean column, what you'll see is just the average. The 3-ish year average for all these plants is somewhere less than 1 pound per trillion BTU. That's good news, right? But the other 2 columns are this not so good news. Every one of these plants out of 7 has had some days in its operating history that are greater than 1.2 pound per trillion BTU. In other words, every one of these plants would violate the MATS limit at some point if we continue to operate them the same way we've been operating them for the last 3 years. These are not uncontrolled units. These are units burning bituminous fuel with plenty of chlorine, with an SCR, with plenty of catalyst, and a scrubber with plenty of water. And we still are out of compliance anywhere from 5 to over 30% of the time. And what is our maximum emission at those plants? The highest 30-day average that we experience, anywhere from 1.3 to 1.9. So we're not way off, but we're off. And you only have to be off a little bit to create a problem for yourself. So So we observe variability in our SCR and FGD units. The next picture I have here is a histogram, or a distribution of emissions from units with activated carbon into a bag house. So this is a Toxicon unit. There's actually 3 units here mixed into the data pool, but it's the same thing, historical 30-day averages, just laid out in a distribution. And what you see is, you've got sort of this normal behavior around about 0.8. So on average, the technology easily achieves the standard. But what we see is this long right-end tail. And that means that we have days, this not normal distribution, where we have compliance issues. And actually, the 99th percentile there is somewhere around 2.25. So we see very similar variability with activated carbon injection that we do with SCR and FGD. So variability isn't necessarily technology dependent, which leads me to believe it has more to do with mercury, less to do with technology. The other thing I want to say is that similar units have been observed to have very different emission profiles. And so, talk about emission profile, what I mean is what does the emissions look like over a long period of time. And this is the emission profile, so the lines are simply the 30-day rolling average lines for 2 different plants. Plants have sister boilers, the same designed SCR, very similar ESP, and the same design scrubber, yet you see very different emission profiles for mercury. The one on the left actually doesn't look too bad. It's only above compliance 5% of the time, and it sort of has a systematic behavior where you see annual peaks in the summer and slightly increasing emissions over time. We can actually handle that because you can plan for an annual peak, it's predictable, and you can plan for sort of a systematic increase over time. That's probably catalyst age or something. There's probably some explanation. But then you go to the next unit over, and it's just madness. None of that sort of normal behavior that you see in the unit on your left, and it's actually out of compliance 26% of the time. So very similar units, very different emission profiles, variability at play. The last thing I want to talk about is the control issue. So why would I say that control performance is unreliable? Again, I want to show some performance here on activated carbon, and my point here is that the long-term performance doesn't always follow the parametric trend. So if you've been to a lot of mercury conferences or environmental controls conferences, you've seen enough parametric trends of activated carbon injection that you could draw them in your sleep. You increase injection rate, you increase performance, or lower emission, depending on how you label the y-axis. Well, what we have shown here is over several years across 3 units, the injection rate versus the emission. You would expect to see as injection rate increases, the emission goes down. Or you would expect if you want to hold the emission at one point that the ejection rate would be very tight. Because that's what we do. We go run a test. We say it takes 1.27 pounds per million ACF to hit the MATS standard. And we put it in our model. Well, what we've observed is that if I want to hit a 1 pound per trillion BTU-ish emission, it takes anywhere from about a half a pound per million ACF of carbon up to close to 3 pounds. And now why is that? I don't know. It's not fuel mercury. Everybody wants to say it must be more mercury in the coal. It's not that. This is consistent PRB coal. The range of mercury in the fuel is very tight. So it's other things, it's process things that drive variability, that make parametric curves only true for a small moment in time in which they were taken. You could also look at it, well, what happens if I just always inject 1 pound per million ACF? Well, in that case, I have emissions anywhere from 0 to over 5. So if you just hold your injection rate, you might be good most of the time, but you see the scatter of dots up the graph. So we see these problems with long-term performance. Talk a little bit about FGD mercury capture, and this was hit on in John's presentation earlier. It's really complex what happens in a scrubber. I'm a mechanical engineer by training, so I don't understand it all, except you've got these multi-paths of what's going on. You've got some mercury just passes right through the water. The oxidized mercury gets absorbed, but then it goes and it starts doing all kinds of things. It can report to the solids in the scrubber. It can stay in solution, and whether it does one or the other, it may or may not reduce. If it's reduced, it may come out of the scrubber. All kinds of stuff goes on that makes it very difficult to predict what is the true capture across an FGD. Remember, 0 to 90%. So this is a complex sort of thing that's inherent in the control itself, which leads me to the next point, which mercury emission is a significant issue. It's real, and I'm not sure that there's a proven commercial solution. Again, I'm not saying that any of the technologies that you might hear about here today are bad technologies. I just don't know if any of them are fully proven out yet. This is just a slide that shows mercury emission to show that it's a real phenomenon. It's not just something that is academically discussed. But you see the load is the top dark line. So you'll see that the mercury emission actually follows load. The bottom line, there's little dots at the bottom you can't really see, which are ESP outlet elemental mercury numbers. They're almost zero, which means if you're capturing all the oxidized mercury, your emission should be essentially zero. But you don't. You see this daily peak where you actually have significant emissions, which that is re-emission. So we see at this site for this week significant re-emission every day. Talk a little bit about re-emission technologies. Not very straightforward. We applied a re-emission technology. It's not important what technology it was. Again, it's probably a good technology. This demonstrates that there's some things to be understood about it. You can kind of see to your far left this first re-emission event that goes up to about 6. The inlet mercury to the scrubber is about 6. So you see this event where all of it's re-emitted. Well, then we start adding the control technology. And because we weren't doing it right, whatever right is, we had these wild re-emission events. So my mercury control technology actually increased mercury emissions. That is a problem. In fact, it didn't just make re-emission the same as it was before. It made it 2 times as bad as it was before. Now you see plenty of time period during the control where emissions are really low. So the technology probably works if it's done correctly. And the point is we got to figure out how to do it correctly because it's not straightforward. These aren't technologies that you just turn on and head to the house. So re-emission technologies might not be straightforward. So what do I want you to take home from this presentation? What's my conclusions? I got 3 here to think about. First of all, you'd be well served if you understood your emissions profile. And that's not very easy because, I showed you emission profiles where one plant was only out of compliance or above the MATS limit, not really out of compliance because it's data from a period where there was no compliance limit. It was over the MATS limit 5% of the time. So if you went out and tested, most of the time, 95% of the time, you would think that you were fine, you were in compliance, your technology was working. The other, even the bad performer, 60% of the time, 65% of the time, you would think you were okay. You really have to somehow be able to understand what that whole profile looks like. We had this great resource because we installed Mercury Sims several years ago, so we have gobs of mercury data. I understand a lot of people don't have that, and so you got to somehow figure out how can I really draw that picture? How can I understand what the true profile is? Not just what it looks like today, not just what it looks like for this week, but what is the real profile? What is my minimum and maximum emissions? Second, I just suggest that you take a very disciplined approach to technology selection. This isn't just like deciding, do I build a scrubber or not build a scrubber? There's more than just sort of that macroeconomic evaluation of your system. You really need to think about each individual plant, what's unique about that plant, and consider that in your technology selection. It takes discipline. You got to get into the details. And then last, just plan for that variability. It's real. We see it every single plant, and it can cause significant issues if you don't have a plan for that. Now, what could that plan look like? We've sort of taken this approach where we want to have complementary controls in our plant. So we want more than one way to control mercury. So if there's variability in my SCR, I can overcome that with some other system. If there's variability in carbon injection, I can overcome that with a second system. The other thing that we've sort of employed as a belief is that we want an engineered control regardless of baseline emissions. It's become known as the knob to turn. What knob do our operators have to turn to deal with those unexpected increases in mercury? So these are just some thoughts that we kick around on how do we deal with the variability and the complexity of mercury. That's my presentation. I guess I have a few minutes for some questions if anybody has one. Yeah, and I think one thing to add to that, because it's been mentioned several times previously here, is as we expect our coal fleet to cycle more, I think it only makes this more complex because you start getting more transients in the combustion process. So good points, thanks.
Just a quick question. If you're looking at the variation in your power plant operation, scrubbers, SCRs, things like that, how much of that contributes to your emissions variability as opposed to, say, measurement variability in your mercury SEMS? Could you care to comment on that?
Yeah, I mean, this is a great debate, and it comes down to sort of three players, and different people want to blame different players. There's the people that want to blame the measurement, right? I can't believe that monitor hanging out of my stack. There's the people that want to blame coal. Oh, well, there's just so much variability in the mercury content in the coal. And then there's those of us that want to blame the process. There's so much things going on in the process. It's hard to say which is which. One of my colleagues made this analogy about mercury SEMS, and I say it way too often, but I'll say it again. He was trying to explain this to some people. Can we believe the accuracy of these SEMS? And he said, if we were to go out tonight after the event, find a local sports bar, and we start throwing some darts, he said, I'm a really bad dart player. So I'd sit there and I'd start throwing darts, and I would never hit the bullseye. Never hit the bullseye. But if I just sat there and I kept throwing darts, and I threw darts for days and days, and threw darts for years and years, if you took the average of all my throws, it'd be the bullseye. Not a good dart player. Any one dart is way off. But when you look at emissions over years, it's probably pretty accurate because you're accounting for high drift, low drift, and all that. So I think in these long trends, we have a fair amount of belief in the SEMS measurement.
You've got gobs of data, and we've got a wad of data. And in our wad of data, I think that we've looked at that mercury data and sort of shrugged at it and felt like it was hard to decide how much O&M effort to put toward it when it wasn't required yet, and how much data QA to believe and scrub on the data. And as a result, our wad of data is very sketchy. Would you say that yours is significantly better?
Yeah, and I'll say as much as I know about it, and part of this goes back to the gushing endorsement that our PSC member gave. So we had a good relationship with the PSC, both in Georgia and Alabama, and we were able to convince them or maybe it wasn't that hard to convince them that it was prudent to install those SIMs that weren't required when camera was thrown out. Prudent to go ahead and install the SIMs and to go ahead and QA and QC those SIMs to a reasonable nature. So we didn't just install them and walk away. You know, the data, I would say we have a pretty high confidence in that data. I'd like to take credit for that, but I didn't make that decision, so somebody else did that good work.
Hi, great presentation. Given the incredible amount of variation that you see from day to day with the same technology or between very similar plants, do you see any value in some of these mercury control prediction models that are out on the market today, or do you feel that it's just really not practically possible to do such a thing?
You know, I don't want to stand up here and say that somebody's model is good and somebody's model is bad. I'm sort of skeptical of them all, and that's just because I know how many times, excuse me, I've been wrong. So we saw emission variability, and we were convinced this is all oxidation variability. And we just knew it, and we were zeroed in on the SCR, and how can we make the SCR a better oxidizer. 6 months later, we saw all this re-emission, and then we were convinced, oh, this is all re-emission, right? If we could just fix re-emission. And so it comes down to, well, if the modeler is a oxidation expert, then they're going to point towards oxidation. If they're more of an FGD, liquid chemistry guy, they're going to point towards liquid chemistry. So I would be careful with any of the models and really try to decide the variability is there. How do I address it from a technology standpoint, and more importantly from an operations standpoint?
Does anyone else have any more questions?
Do you have any perspective on the sorbent trap methodology versus the SIMS methodology?
Yeah, this is another issue that demands great debate within our company, because without question, sorbent traps are easier to operate, and they're more reliable, and they're more precise. That's without question. I don't think anybody would argue that. But they don't give you instant feedback. And so, you know, you can stick the sorbent trap in there, and you can run it for up to 14 days, I think, under the rule. And then at the end, you pull it out, and you cross your fingers and hope you're in compliance. So, personally, I feel very uncomfortable driving the ship blind. So I think the feedback, the process control you get out of SIMS is of paramount importance to actually controlling these technologies. But there are great advantages to the sorbent traps. They're simpler and a little more reliable. I don't know if that clears anything up, but I'm a big fan of SIMS. If not for compliance, at least for process control. All right, I appreciate y'all's time and the excellent questions. Thank you.
Oh, right. All right, our next speaker is Bob Beck. He's the Vice President and Chief Operating Officer of the National Coal Council. I will say this, that I used to work for Bob a long time ago in a galaxy far, far away. So that's just a little bit of information there.
Thanks, Mike. First of all, I have to thank Eloise for loading the slides, and Mike for at least getting them to this point. I need to go backwards. How do I work this thing? I am the guy who emailed Tim this morning about what is Twitter and what is Facebook. So this is proof positive. Okay, there we go. Okay. All right. I went to the Stu Dalton School of Public Speaking, which means you got to have slides when you speak. Everybody at EPRI does, and they used to actually be drawn out overheads. I'm that old, and now we're into this PowerPoint stuff, which is kind of cool. But back when Mike and I were working together at the Edison Electric Institute, I used to go up to the hill with a pocket full of quarters. Actually, my first year there, I went up with a pocket full of dimes because that's all it cost. And every time something happened, you'd sprint for the 3 payphones that were in the Rayburn House Office building to actually call back and say, hey, boss, something happened. Well, now, geez, you know, you got all this neat stuff that works. And so it's really good and to some extent, which means you're always plugged in, and it's really bad to the other extent, which means you're always plugged in, and you can never get away from anything. But I know it's not June 22nd. In fact, it's November 14th. But we did a study dated June 22nd. This is it. This is the hard copy executive summary with a CD in the back. It's 200 pages long. And as Stu Dalton will tell you, I couldn't engineer my way out of a paper bag. I'm like Mike Morris and Dave Ratcliffe. I'm a fisheries biologist that got started doing 316A and B work back in 1974, ladies and gentlemen. Yes, what goes round comes round, and it's back again. Let me put this down for a second. Anyway, I brought 5 of them because I couldn't bring all the 1,000 that I have back in the office. And it's also on our website. So we do have 200 pages of really high-quality engineering that's going to back up everything I'm about to talk about. That's us, commercial. Another disclaimer. For the most part on this study, I'm here to talk about it from the National Coal Council standpoint. When I get into the really neat stuff about what's going on in Washington, that's just me speaking as somebody that's been up there for way too long, since 1981, working on this stuff. Personal members appointed by the Secretary. 3 people this morning that were on the panel, Ken Namath, Stu Dalton, and Mike Morris, are all current members of the council. It's that kind of quality of people that we have on the council. They park the guns and colors at the door when they come in. They have to take off their corporate hat, and they have to come in as just experts in the field. We're a FACA, which means we're open, transparent, and just like every other piece of government, right? We're very transparent, open. We have 112 members that keep me really busy because it's just me and Pam. We're a 2-person shop back in D.C. Dick Bajura, a longtime professor at West Virginia University, was the leader of the study. Fred Palmer, who's the executive vice president at Peabody, chairs our technical committee, which we call the Coal Policy Committee. Frank Clemente, also a longtime professor at Penn State, and we had a whole bunch of really intelligent people working on this thing. It was requested a while ago, last year, and Secretary Chu, a strong supporter of coal, asked us to do this. What, no giggles, no nothing? You don't understand sarcasm when you hear it, sorry. I know, it's 4 o'clock and we're looking for the cocktail hour. And you heard Ken talk a little bit about CCUS and enhanced oil recovery. My good friend Chuck McConnell, who's the Assistant Secretary at DOE right now for fossil energy, is a huge proponent of this. And so we were working on just trying to figure out, could this stuff work? What does it mean? What could it mean? Et cetera, in terms of jobs and creating fuels and other things. What we found was that, let me ask you a question. In 1930, where do you think the actual world production of oil was at its peak? What was at that time the Saudi Arabia of oil production, 1930? It was in the thriving metropolis of Findlay, Ohio, okay? Findlay College, their nickname's actually the Oilers. When I was in Thomas More College playing basketball, we used to play them. Got some of the worst homer jobs up there you ever wanted to meet in terms of officiating. But it's also the home of Ben Roethlisberger, so you can file that one away too. And you know what? About 70% of all the oil that was there then is still there. They only took the easy part. John D., you know, when he was living in New York and arguing with the railroads on moving his oil around, Standard Oil of Ohio and all that stuff, it just took the easy stuff. When it got tough, they went down to the easier, more sandy, more porous soils down in, Louisiana, Arkansas, Texas, Oklahoma, etc. So we think there's still a whole lot of stuff there. And at $85 a barrel, we think it's potentially can be recovered if you capture CO2 at power plants and put it in the ground and push up the oil, okay? They've been doing it. Denbury, who was a big player in this particular study, has been doing that for about 40 years. They have an excellent business model. They make a lot of money doing it down in the Texas, Louisiana, Mississippi, Arkansas part of the world. But they like very much to do it in Ohio, Indiana, Illinois, West Virginia, Kentucky, et cetera. Because why? What constrains the whole problem or the whole process of enhanced oil recovery is the limited availability of CO2. That we just don't have it. And what they use now, they mine. They actually dig down, bring it up, pipe it from Colorado, Wyoming down to Texas and use it. So why not come up with, all the CO2 emissions that we have, capture them, and then use them in enhanced oil? At $85 a barrel, it's attractive. When we were asked to do this study, the price of oil was $140. Today, I just came down after the President's news conference, and it's about $86.80. But because the Israelis just wiped out 2 Hamas leaders with smart weapons or bombs or whatever this afternoon, the experts are saying that within the next 3 months, possibly even the next 3 weeks, we could see oil at 115 because we are becoming much more unstable in that part of the world. The Israelis have an election. Netanyahu is doing his thing, and he's spoiling for a fight with the Iranians, so we'll see what happens. In any event, it's 85 today. Who knows where it's going? It's attractive. The President has stipulated a goal for the United States to reduce our emissions by 80%. Actually, it's 83%, but the 3%, who's going to quibble over that? By 2050, and unless there is a tremendous advance in modern medicine, I won't be here to see that. But you can see that there are opportunities in terms of recovery and in terms of using CO2. We have about a lot of billions of metric tons of CO2 available. Currently, we only use about 2. So there is potential for great increase. We could also provide about 30% of our nation's liquid fuels by 2035. Right now, that's not a very viable economic plan to convert coal to liquids, but you certainly can do it. The Germans ran their whole World War II effort on it, and the South Africans truly are leaders, and they're exporting it and licensing it in China even as we speak. So it is doable. It is a question of dollars. But if we did it and we created a way to reduce capturing CO2 emissions, which I've got Stu working on even as we speak, to get that down to something feasible that we could afford, you could then create a robust system of pipelines similar to the airlines system of hub and spoke. You could have smaller pipelines to one big facility, and then you could pump it from that facility in transcontinental or at least long-distance pipelines. We know how to do that. We can do it. It would put lots and lots of people to work, not just in the highly skilled jobs of engineering and what have you, but also in the construction, the operation, just the monitoring, the security systems. All of those kinds of things are available, and this is the kind of thing that we think could be in place by 2035, certainly out to 2040, 2045, and 2050. So that's it on that particular thing, and I am going to, I'll be happy to take questions about the actual study itself, but as I said, there are 200 pages of actual text with another 70 pages of appendices attached on the website. It's all one word now, nationalcoalcouncil.org. Click on the information button, click on the studies for download, click on this one, harnessing coals, et cetera, et cetera. So that was part of what I was asked to do, is what is my vision of the coal industry by 2035 or so. The vision is robust, to say the least, because in order to do anything in this country to control CO2 emissions, you're going to have to do it across the board on all fossil fuels. The first quarter of 2012, the electricity portion generation that's using natural gas for the first time ever created and emitted more CO2 than did the coal portion. Now, we're not happy about that because that means our share of generation went down and theirs went way up. But it's a fact that eventually we're going to have to put CCS and hopefully CCUS on a lot of power plants. Again, you've heard retirements, 40, 50, 60 thousand megawatts. We have about 325,000 megawatts of coal out there right now, give or take, depending on how you want to add it. Might be 320, might be 322, but we got a lot of it. I think about 5 or 6 years ago, we did a study, and the estimate was that we would actually retire about 70,000 of those megawatts. So we're actually below the number that we actually thought we were going to be retiring. And a lot of those units need to be retired and should be retired. The sites are going to continue to be used in some way, shape, or form because the only thing harder to build than a power plant in the United States these days is a transmission line. It's just a very difficult process. So if you've got your interconnects already there, then why not use it? So we're not surprised by that. I'll throw a couple of more stats out at you. In the last 5 years, China has built our system. In the last 5 years, they've built 325,000 megawatts. In 5 more years, they're going to build another 325,000 megawatts. They produce about 1.5 billion tons of coal a year. We produce about 1 billion. They use about 2.5 billion. So they could import everything that we produce just to remain level. And that would leave us with none, which obviously isn't feasible. But that gives you an idea of what the export potential is. And they get a lot of coal from Mongolia and Australia and Indonesia and places like that. But we have really upped our exports. When I started 15 years ago, we didn't even talk about exports. It was less than 10,000 tons a year. I mean, 10,000 tons a year, nothing. We're at least up around 100,000 now, and that's 10% of what we do. So that's not a bad increase, and it's growing all the more. So we're now going to move from the sublime, all facts, data, engineering, to the ridiculous, which is the other thing I was asked to talk about, and that is, what the hell happened last Tuesday? So I'll give it a shot. And in case you haven't noticed, nothing. It's the same as it was the Monday before the Tuesday. It's all the same. There's a couple of new senators, there's a couple of new House people, folks are retiring, resigning, what have you. But for the most part, it hasn't changed much. But that doesn't mean change isn't coming, okay? We're going to have change and hope, or whatever, hope and change. I can't remember what the slogan was, but that's what it was. We are, within the White House, there's no more czars, okay, or czarinas in Carol Browner's case in the first 2 years of the previous administration. I think they've learned that from that standpoint it doesn't work, but they're still very important people. Todd Stern happens to be one of them. He's principal negotiator for all of the international climate change stuff in the UN. I know nobody pays attention to it anymore, but it's still going on. The follow-on to Kyoto and all that other stuff is still going on. And Todd was one of the lead negotiators back in the 90s when I was still at EEI, and he was involved in the Berlin Accords in 95 and the Kyoto Protocol in 97 and all that kind of stuff. So he's still there, but I'll tell you what, the Greens are not happy with him. So they're trying to push him out, and so there might be a change within that kind of a mid-level White House guy. Although how mid-level it is subject to someone's interpretation, because he does actually have an office in the West, in the West Wing. So that's going to go on. I have a prediction, I'm sorry. Associated with the White House policy, because we know policy trumps finance, which trumps technology. And I agree with that. Since I'm in the policy level, that puts me at the top of the food chain. I like that. So, thanks, Stu. I'm going to borrow that every chance I get. But my prediction is that the northern portion of the Keystone Pipeline route will never be approved in the next 4 years. It might never be approved, but I'm just going to go out 4 years, okay? It just isn't going to happen. The southern part has already been approved, but we're going to keep, doing this dance back and forth. And the green community is probably going to carry the day for the simple reason that elections have consequences, and we had an election. So I just don't see it happening. And in fact, I talked to David Hawkins, a longtime associate and adversary, I guess you might say. David is with the NRDC, and he was assistant administrator at EPA for air and radiation during the Carter years, and then from 80, 81, he's been at NRDC, first on clean air stuff and now on climate change stuff. And he basically said that portion of the debate, their sector of the debate, they really don't even care if the Keystone Pipeline gets approved or not. They're using it as practice. And as Allen Iverson once said, practice. We're talking about practice. But it was practice for defeating all the other pipelines that are going to be needed to move CO2, to move natural gas, whether it's fractured or however you get it out of the ground, oil after that. So this is a long-term, tough nut to crack from a policy standpoint, and we're going to need some political will to try to get that done. Had a conversation with the president from Williams Energy Company, and they're a big pipeline operation. He said, in 3 years, we're going to be squeezed. We don't have pipeline capacity to move all this gas. We don't necessarily like the price at $3.50, but the price isn't going to stay at $3.50 when you don't have pipes to move it to where you want. We're creating demand now, and we're losing our butt because it's $10 million a well. But they are going to eventually raise that price, and they are definitely going to export. As I think Stu was saying, it's $14 an MCF over in Japan, and in Europe it is what it is. So those things are going on as well. But keep an eye on that, because that'll be interesting, and you can see whether I know what I'm talking about or not. But I really don't care. I'm going to retire next year anyway. So, again, that was just me. All right, other things up there. I actually have some notes here that I can't read without my glasses. So in deference to Tony Kornheiser, I'm going to the glasses. The Energy Department, Secretary Chu is probably not going to stay much longer. He's an R&D kind of guy. He got his brains beat out over Solyndra. I think he's tired of that. And he's probably going to go back into academia. So who's going to take his place? Well, since it's my one and only customer, I really care. And there are some really cool guys and people in general that are being promoted. One is former Senator Byron Dorgan from North Dakota. Boy, would that be great. The guy actually knows a lot about energy because of the Great Plains Energy Complex and all the stuff they're doing up there. Katie McGinty has been mentioned. I don't know if any of you know Katie. I happen to know her pretty well. She was the chairman of CEQ for all 8 years of the Clinton administration. Prior to that, she worked on Al Gore's staff up in the Senate. Very intelligent, very engaging, and has leadership qualities that were honed even further when she ran the Pennsylvania Department of Natural Resources for Governor Rendell, who is, as you know, kind of a real leader within the Democratic community. So Katie's going to have a lot of support. She's got a stunning resume, and it would be an interesting time for me for the next year or so if she were to actually become the secretary. But a real potential there. Kathy Zoy, I don't know how many of you know Kathy. She's been around a while, worked out in Massachusetts on electric vehicles way a long time ago, again, when I was at EEI. But she's a pal of Al Gore's, too. She's the former CEO of his Alliance for Climate Protection, and so could get some support, especially from a conformational standpoint. She doesn't carry a lot of baggage and would probably cruise through. I think all three of those folks would cruise right through. There's some flyers that I've heard about. Dan Riker, who is his entire career has been with, I believe, with Sierra Club, might be Environmental Defense, I can't remember, but for his time in the Department of Energy as Assistant Secretary for Renewables in the Clinton administration, stayed there all 8 years. So he's potential. And in all deference to the folks from Duke, actually heard Jim Rogers' name mentioned. I know Jim pretty well as well from my days at EEI when I actually knew him when he was the CEO of Public Service Indiana before he got the company that I used to work for, which was Cincinnati Gas and Electric. I don't think Jim has a lot of interest in it, and confirmation is a very difficult thing. But I've seen his name out there. Now, one thing you can be sure of, because I said it, and I thought these people might be, none of them will be there. There'll be somebody else. Somebody will come out of left field and they'll put somebody in there. One last area of concern from our standpoint and from the coal industry standpoint is Department of Interior. Former Senator Ken Salazar from Colorado is the secretary. Mixed signals. He'd really like to stay, but he'd also like to spend more time with his family. He's been in Washington quite a while as senator and now as secretary. He's not going to run for president, so what's left, and so he may or may not hang around. If he doesn't, his current deputy, a guy named David Hayes, who I wouldn't don't know him if he ran over me, but apparently he's very highly thought of within the DOI group. Certainly with Salazar's backing, probably would have no trouble with confirmation. He's already been confirmed because you have to be if you're Deputy Secretary of Interior. So a name that you might think about. Also, retiring Senator Jeff Bingaman from New Mexico has been mentioned. It's traditionally a western post. New Mexico, last I checked, is in the western part of the United States. And he would be an excellent choice. Really, really a good man with great talent to compromise and work through really contentious issues to accomplish stuff. So he might be it. I've also heard that the former governor from Wyoming, Dave Friedenthal, might be a candidate. Again, a very good man, has worked on some things in terms of coal and promoting coal within the state of Wyoming, yet still being, having a nice green, if you will, tint to a lot of his policies. And there's a couple of other folks that have been mentioned as well. But it'll be interesting because these questions, or some of these questions, were asked of the president this afternoon in his first news conference since the election. And he basically said, I'm not telling you guys what I'm doing. I've got a lot of high-quality individuals, and we'll kind of go from there. So that's kind of an overview, some things to be on the lookout for. I know tomorrow, I'm not sure exactly how it's going to be set up, but I'm part of a group of various roundtables and discussions, and I think I'm supposed to talk at length about all of this, which means I'll probably just read the paper tomorrow and see how all of it's changed, and we'll go from there. But anyway, that's kind of like I said, from the sublime to the ridiculous. I just want to finish with one comment. When I first started lobbying the Hill in September of '81, the chairman of the Environment and Public Works Committee was a guy named Bob Stafford. God rest his soul, he died some time ago. Very dry New England wit. He would always refer to himself, not as Bob Stafford or Bob or Senator Stafford. He would always refer to himself as the senior senator from Vermont. Well, the senior senator of Vermont has an opinion that states, and that kind of thing. But he was kind of a cool, just laid-back, dry-witted kind of guy. And to go along with Stu's, policy trumps finance, which trumps technology. He once told a story, kind of a humorous story. I wouldn't call it a joke, but a humorous story about a young guy who had just graduated from college. He had his backpack on. He was out, and he was hiking through the woods in Vermont. And he got lost. He came to a crossroad, or a fork in the road. And of course, as Yogi Berra always said, if you come to a fork in the road, take it. He got to the fork in the road, and it said, he was trying to get to the Capitol, right? So one arrow said to the right, it said, to Montpelier. And the other arrow to the left said, to Montpelier. So he was in a quandary. And he looks around, and he sees his old man up there rocking away on his rocking chair up in his log cabin. And he looks up, and he says, hey, sir, hey, old fella, can you help me out here? He said, you look like you've lived here all your life. And the guy rocked back and forth and he said, "Not yet." And so the guy says, "Whoa, whoops, maybe I hit a nerve. Well, hey, let me tell you, I need some help. I need some help. I'm trying to get to Montpelier. Does it make any difference which way I go, to the right or to the left?" And the old man looked at him and said, "Now, to me, it don't." And that just kind of puts into a very short microcosm, small microcosm, how our Congress ought to be working. There are lots of ways to get to where we want to get to, not just two. There are lots of ways. And if we could just have a little bit of humor and a little bit of self-deprivation and just step the egos down a notch and actually try to get something done, we probably could. But we won't. Thanks. I'd be glad to answer any questions, but I know it's been complete comprehension, so thank you. I will answer any questions if there are any, either about the study, which I'll defer to Stu about, or all these wild conjectures on politics. Like I said, oops, I got one in the back. Yes, sir.
Do you see any changes in the committee chairs that could affect us in this industry?
Any chairs in the Congress?
Yeah.
Yeah, there's definitely going to be some changes in chairmanships because I don't know if you recall, but back a while ago, the Republicans, when they took over control of the House, not for the first time with Newt and Du Bois and the contract with America, but just a couple of 4 or 5 years, whatever it was, just a few years ago, they established their own term limits on how long you could chair a committee. They used John Dingell as an example. Congressman Dingell was the chairman of the Energy and Commerce Committee probably since before I was born until, about 1990 or something. And before that, it was his dad, I guess. But, their thought was, we're not going to term limit ourselves to being a member of Congress, but we're going to rotate the chairmanship. There are some folks that are bumping up against that. It's not going to really change the policy of the various committees or subcommittees. Because it's almost like musical chairs. Because, when Joe Barton stepped down as Energy and Commerce Chairman, he became chairman of the Oversight and Investigation Subcommittee, which is nominally more powerful than the whole committee itself. So, you just slide people around. But, Fred Upton, Ed Whitfield, Barton, those guys, they're still going to run the Energy and Commerce Committee no matter who sits in the chair and who sits, in the other things. On the Senate side, there will be an interesting change, and that is on the Energy and Natural Resources Committee. The Environment and Public Works Committee is going to stay the same. Senator Boxer she'll still chair it, I'm sure, and Jim Inhofe will be the ranking minority guy, and they're going to have to go through the metal detector before they go in the room, before they have any discussions, because they don't necessarily get along on the policy part of it. But Jeff Bingaman is retiring, and between Jeff Bingaman and Pete Domenici, the state of New Mexico has held the chairmanship of the Energy and Natural Resources Committee for something on the order of 28 years. And so for the first time, there won't be a chairman from the state of New Mexico. And when you think about just the population distribution of the country, that's amazing. I mean, it's a large state, but it's very small population. And where that's going to go will be interesting to watch, to see which Democrat would like to get that chairmanship. It's probably still going to be a moderate, middle-of-the-road kind of guy like Senator Bingaman was, like Senator Domenici was. But it'll be interesting. The shift off that committee, a couple of years ago, Senator Bunning was shoved off. So it got to be even a more moderate group. The problem is that even though that committee gets along and works together quite well, they can't carry the day on the floor because the two guys, the majority leader and minority leader, basically can't stand each other, and it's a tough dichotomy to try to work through. I mean, witness the fact that one guy has held up the Yucca Mountain thing forever, and will always hold it up as long as he remains as not just the majority leader, but a senator. It'll, given all that, from our standpoint, I don't know who mentioned it to start this morning. It's going to be business as usual from the energy side of things, which means probably nothing much on it, from a legislative standpoint. So all the action is going to be over DPA. Okay, thank you very much. Hopefully we're still on time. Thanks, Mike.
Hello, my name's Keith Moser. I'm the Innovation Manager for Exelon Generation, and I've got Mark Vanderhelm with me, the Director of Generation Development and Alternative Energy Development. And what we're going to talk about today is net power. We just merged with Constellation Energy, and I don't want to spend a lot of time with this, but we have become quite large. A little bit more detail: power generation, 35 gigawatts of capacity. Constellation, which does a lot of our competitive energy pricing. And then utility parts: ComEd, PECO, and BGE. The part that I do want to spend some time on is really where we're at in generation. For the most part, we're still a nuclear power company, 19 gigawatts of nuclear power. But our goal is to be one of the nation's cleanest fleets from CO2, SO2, and NOx. Now, we have some challenges. Our newest nuclear power plant is older than the oldest nuclear power plant in South Korea and China. We are having problems with our fleets aging. The other issue that we're starting to have in many cases, single unit nuclear power plants are not nearly as cost effective, and consequently, with some of the challenges we're getting in marketing and natural gas, it's difficult to make a good return on those. I do want to spend a little time on this. Nuclear power. At this point in time, this was when deregulation was happening. We didn't have to operate very efficiently under the old regulated markets. We got very serious with deregulation. We started changing out management, having an improved management model, and really getting our processes down. But right now, there's not much more we can get out of our management model. We're pretty much at where we need to be with capacity. So we're starting to look at what else is out there. A new nuclear power plant like at Victoria is such a big bet. You know, even with our market size, capitalization, the new nuclear power plant would be about half of our market cap. Take about 5 to 6 years to come online. Huge bet for any CEO that would want to make that kind of investment. The other thing that's happening is when we start looking at these small modular reactors. They're great technology. I really love them. We've looked at over 76 different concepts. But because of their size, the economies of scales just don't fit into it, and your installed capacity factors are so high. And then on top of that, you have to have about the same size of staff as you do at the larger power plants. Makes it very challenging to come up with a business case. When I first got real interested in carbon capture and some of the technologies that Mark's going to talk about today was when the DOE first came out with the RPE program. I noticed that NALCO is one of the sponsors, but Argonne Labs and NALCO were looking to get some grants, and they asked us to get involved. The program they were going after was resin wafer electrodeionization of flue gases for carbon capture. And it really opened my eyes on what was possible. That research went on fairly well. It made some important contributions. But there was still this problem of how do you make it efficient enough to really make money. And then when I started seeing what was happening with Net Power and how you could have that efficiency, have the fairly low cost for building out the plant, and have the ability to not only capture the carbon, but put it into some other process, whether it's oil recovery, growing algae for biofuels, got me really interested. And I'm going to turn it over to Mark to go over the technology slides for how Net Power works.
Thanks, Steve. Appreciate it. So what I'm going to be talking about today is, I think, good news for the entirety of the industry, potentially with one exception, which are the vendors out there talking about control technology. Because what we're talking about today, and hopefully in the larger perspective of things, people will jump on board and realize what a positive impact this technology has potential for. But what we're talking about is a thermodynamic cycle, which is transformational to the industry in terms of the core technology, and if it bears itself out in terms of cost, it's transformational in terms of how we create electricity going forward. Exelon is a unregulated utility, which means when we look at building new generation, we're looking at doing that at an economic, with an economic signal that would allow us to do that. So our bar, as I think most people have understood, is a combined cycle unit, is the next cycle, or the next technology that one would build, especially in this gas price environment. So that becomes the bogey that Net Power compares itself again in terms of the aspirations of what we want to do with this new technology. It's low cost, uses natural gas, can use coal or biomass, but we'll get into the variations of that. High recycle of the CO2. It's using supercritical CO2, and it's oxidizing, or it's an oxy-combustion process directly using oxygen, so thereby eliminating a lot of the issues around having air in your combustion cycle. Key aspects about the technology that I'll go through some additional slides after this are listed out here. You get a lot of benefits in terms of the capital, because you're talking about a single gas turbine, and you're talking about low temperatures. Obviously, in the combined cycle space, the benefits, as we've seen going from the 6,800 high heating value heat rate down to 6,300, have been coming at with these higher temperature alloys and higher temperature flame temperatures associated with them. We're also talking about a higher pressure working fluid, which enables us to have a smaller footprint. The lower capital and operating costs, and the potential, as previous speakers have pointed to, Robert pointed to, in terms of CO2 and use for enhanced oil recovery, allow more of a baseload operation, which fully which further improves the economics. Like most technologies can use water cooling, actually, because it's combusting CO2 with oxygen. Water is one of the byproducts, so it's actually creating water. And because this is a core technology that is using the CO2 as a working fluid, if we can meet those capital cost goals that have been laid out and efficiency goals laid out for the technology, then you have a set of technologies that can improve the other types of generating technology that exist out there, and we'll go through a few of those in coming slides. Who's involved in this? The technology is a NET Power organization that has the IP around it, and they put together this team. Exelon's role here is associated with the first objective, which is put a pilot plant in place, and we're looking at the permitting, the development, siting aspect of things. My role in Exelon is leading up development, so then leading up that portion of this team. NET Power, as I mentioned, has the IP. The technology came from an individual that was previously at Air Products, technology lead at Air Products, and there's some, when people look at this diagram that I'll go to on the next page, a lot of people that have tried to solve some of these problems, you can see the light bulbs go off in their head as they see some of the solutions that are there, that have been demonstrated, and that we're hoping to put into, move from computer models into an actual pilot plant. Toshiba is tackling one of the critical aspects of this, which is designing the combustor turbine. Shaw is both an investor in the NET Power technology, as well as providing the engineering, procurement, construction services for the pilot, and then for the commercial units going forward. And Jeff Rees is providing a lot of the financial modeling associated with the technology. So this is a oversimplified diagram of what we're talking about, but fundamentally you've got, is this a pointer? Okay. Fundamentally you've got natural gas. Well, first of all, let's start with the air separation unit, creating the oxygen, natural gas, going into the combustor, then the turbine, reheat, cooling down, pull the water off, CO2 cycles around, compressed up, back to liquid, pumped, that CO2, and we'll get into some of the other applications. That compressed CO2 now is pipeline quality, ready for direct sequestration, and the remainder of the CO2 goes back as the working fluid for the cycle. The objective in terms of cycle efficiency is 59%, and that's the higher heating value, just to make sure that we're all clear on that. 100% carbon capture. This is a rough sketch of the work that Toshiba is working on with respect to designing with the two critical components, this turbine, this combustor and turbine. The main focus here is, when they're designing this, they're focusing on the pilot plant, so not necessarily optimizing for the 25 megawatt size. They're optimizing around creating a demonstration equipment that they can then scale up to the commercial size, which you're looking at, the 250 megawatt turbine. The other applications associated with this technology are listed out here as well. Not only we're focusing, this consortium is focusing on using natural gas as the fuel, as one can recognize, you dig into the technology, being able to use coal and gasify coal, biomass, gasify biomass as well, that can then be used as fuel as well. Obviously, you're not going to get necessarily the same heating, same efficiency associated with those because of the gasifation impact on efficiency. You can also use the technology as a topping cycle on top of any of your traditional units. And the heat required for gasifying liquid natural gas, you combine this facility with the necessary heat for that. That heat can then improve the efficiency from that 59% to 67% for this cycle. If you combine it and co-locate it out in West Texas or some of the other places that our previous speaker, Robert, was talking about, harvesting CO2 from places in Denver and Wyoming and sending it down to West Texas for enhanced oil recovery. You can co-locate this facility right there at the fields and get improved economics associated with not only the value of the CO2 that you get, but also some of the thermal aspects, the gas that comes off as a byproduct of the oil. And you can also combine this with solar technology and use solar as a supplement to the natural gas as a fuel. And that solar also will improve the efficiency. You have to make the efficiency and the capital work simultaneously. So this is another slide just on the efficiency aspects of it. So the target efficiency for the base technology is 59% using natural gas, using coal, the 55%. Compare that to what's out there currently in terms of the zero carbon capture. If you then layer on an expectation of converting these technologies into technologies which have CO2 at the same level of quality as coming out of the system, their efficiency is further degraded. So you have a better approved input, approved demonstrated efficiency of this technology over those. And with that's driving a lot of that efficiency and capital improvements, that you're fundamentally using higher pressures, leaving smaller components. A lot of the components that you traditionally associate with a power plant aren't there. Obviously, the steam turbine and all the piping associated with the HRSG and so forth that you'd have for a combined cycle. You do have the air separation unit, which is an added capital item that offsets that. But there's a significant amount of reduced complexity associated with the cycle that's being dug into and we're building a pilot plant around. The footprint for something like this is considerably less than a combined cycle. And that also then translates into potential benefits around modular construction, being able to put larger, more complex systems, manufacturing those in the plant and not doing them out in the field. We translate this into that combination of efficiency and capital cost and get to the metric of the LCOE, or the levelized cost of energy. You end up with these type of comparisons. So this is a comparison of a number of situations I'll walk through, but just make sure we understand the levelized cost of electricity. You want to incorporate the capital and the variable components associated with creating that electricity, and that's quite often how people look at that next most economic way of generating electricity, and that's the bar that we're looking at. On the left, we're showing what the incremental cost is from an LCOE perspective for all the upgrades associated with a coal plant, including if it's required to actually do CO2 capture. We show the net power, and that's assuming essentially fully depreciated assets, so there's no capital associated with that bar. So that's just the variable component and the capital associated with any of the upgrades. For the middle bar, that represents what Net Power technology is looking at in terms of the LCOE. And then if you want to get a new combined cycle to the same quality level of CO2, you also have to do carbon capture associated with that. So when you incorporate both the variable costs and the capital costs associated with that, then you end up with also a higher cost solution if you're in an environment where carbon capture is expected. Without carbon capture expected, again, the goal is to be on par or slightly better in a new combined cycle. So in terms of actual next steps associated with what this team is working on, the general objective is broken up into 2 buckets. The team is working on a pilot plant for which we're doing the design this year. Most of the construction in 13 and 14, and then looking at operating in ladder 14 and 15, again for this small 25 megawatt plant. And in parallel to that, as time and resources allow, the team will be looking at applications outside of using natural gas as the fuel for the technology. Looking out into the future beyond that, then you take the learnings from the pilot plant, translate that into scaling it up to the 250 megawatt plants, and begin to build out those commercial units to the extent that we can demonstrate again that the efficiency and capital cost components have met the targets that the team has laid out. And also build out the other uses that I went through in the previous slide. In terms of where we are today with the team, one of the two critical, the objective, let me first say, for the pilot plant is to not only build it, operate it, but get some continuous operation out of it to demonstrate that you have degradation, which is on par with what you'd see with other technologies. And also, when you have that pilot plant, you can do all the system testing. You can make sure that you've got the right understanding of chemistry, the right understanding of operations, the right understanding of safety and the safety aspects that are critical to a new technology, and begin to optimize your cycle from there. Where we are today in terms of the team objectives, obviously this consortium was put together this summer, and an agreement was completed over the summer. The pre-feed, essentially the engineering design study, is now complete. Toshiba is well on their way in terms of designing the combustor turbine, and December anticipating a combustor test. We'll see what those results get us in early January. That's my presentation. Questions? Yeah.
Can you comment on 100% carbon capture and what is the cost adder?
The cost adder for 100% carbon capture. The cycle produces what I would call pipeline quality CO2. So there's no additional cleaning, pressurization, anything else, because the cycle itself is CO2 in that cycle.
So your turbine is rejecting then into pressurized CO2? Like, are you guys going to take it into like low pressure and then pressurize it, just tracking it efficiency-wise, because you're injecting it into the atmosphere? Because I know like regular combustion turbine, essentially the atmosphere, so this you'd be going into some back pressure.
Yeah, the bottom cycle I think is at 30 bar. The issue there at the lowest pressure point is actually not liquid, so compressing it back to liquid and then pumping it up is more efficient. But yeah, I mean it's a closed loop cycle. Yeah, so just I think your first question, it's a closed loop cycle, right? So you don't have any. The critical aspect about this is making sure that CO2 remains in the system in the flow. So there is no outlet out into the air.
I guess what I'm saying is you're going to take somewhat a little bit of efficiency hit, because if I take a turbine and I just exhaust it to the atmosphere, that's lower pressure than putting it into a pipeline.
The actual cycle drops down to a lower pressure. Go ahead, Dave, if you want. But the actual cycle drops down to a lower pressure, then it's brought back up to pipeline equality. But
yeah, so this is it's a highly recuperative cycle. I'm from NET Power. It's a highly recuperative cycle, so you actually want to have a low pressure ratio across your turbine rather than, say, a steam system where you want to expel beyond atmospheric. You want to get closer to a vacuum. We maintain that back pressure and then recuperate that by, as Mark said, retaining that supercritical nature of CO2. CO2 is very nice in that when you get up to higher pressures, when you get above the critical point, you can utilize a pump, which requires a lot less efficiency. And so the efficiency gains of using that low pressure ratio turbine is pretty phenomenal.
Thank you. Yeah, so we've broken this up into essentially 4 phases. Completed the first phase, which was predominantly around completing the pre-feed study in terms of assessment for capital costs and so forth. The second phase is predominantly around siting and permitting in this combustor test. Then you get into, and completing the overall feed study. Then you get into late 2013 and through 2014, we're actually doing construction. Late 2014 into do a lot of construction as well as testing. Go through a pretty significant testing phase. So by the time you're at late 2014 through 2015, you're actually looking at operation for the facility. Do you have a site? Yes. It's not public, so I apologize, but yeah. What's that? A design for. They're working on the turbine as we speak. Yeah. But I mean, obviously that is the challenge. I mean, it's absolutely understood. Again, this is the space of new technology, space of extremely challenging problems. Yeah.
About 5 years ago, I watched the small combustor out at Clean Energy Systems operate and about a month ago, I was out looking at their larger operation, and they're building a couple hundred, something that's going to scale to a couple hundred megawatts. They expect to finish their first firing on that turbine in January. They're about a year ahead on their AARA project. It's a different cycle, it's a different way of putting things together. Some of the pieces are similar in that they're trying to have zero emissions and look at CO2 utilization, and it's an oxy fuel. And some of the questions that have come up are things like purity, and because oxy fuel inherently has excess oxygen in the original composition of the make, and then there has to be something in the cycle to clean it up to the quality required. Because I stood up at Waybird and they said over 100 ppm of oxygen that shut down the system because of they have to, because otherwise bacterial grow in the EOR injection. So any comments on purity, oxygen content in the CO2?
I think it's very much recognized as an issue. I mean, I wouldn't say that it's not observed as an issue. I've seen some of the stuff that Clean Energy Systems has run into. And yeah, I mean, understood that, it's one of the challenges that are on the table in terms of cleaning that fluid back up as it goes through the working cycle. But fully understood that the challenge here is this closed-loop system, sufficient purity of the CO2, and the implications around any of the impurities. Other questions? We will have both myself and Keith, as well as Dave Freed and Lee Elder, who are in the back of the room, will be participating in the roundtables tomorrow. So as people come up with more questions, definitely interested in fielding those and continuing the dialogue. Okay. All right. Thank you.
Well, that concludes today's session. I'd like another round of applause for all the speakers today. I think they were all excellent. And I guess at 5:30 there's a reception. I assume it's out here. Is that correct? Okay. See you all there.